All right, so now we're going to process the signal we just measured. But before that, I just want to make sure you understand what RMS is. And so you might have heard of it. All right, and let's see if this will actually measure. And I don't think this tool actually measures RMS. All right, but that has a peak to peak, and if you've taken circuits, you know that the RMS of a sine wave is about 0.7 times the amplitude, right? The thing about what it does is it squares all the values, averages all those squares, and then takes the square root, right? Because that's the best way to um, kind of characterize a signal compared to a DC. All right, so we'll just put that back on noise. And so we've already saved that file somewhere, but this is the Python code. There's a link, right? And just some things that you have to do is it actually finds the RMS. The thing is we have to take out that DC part. Otherwise, all we would be really getting is mostly that DC signal. So the code works. And essentially, what you can do is cut and paste this code into just Colab. Just make it, just Google Colab, right? And then do a new notebook, and then cut and paste this file, right? And it actually should run because I think I published this particular Google Doc everywhere. Now, you have to make sure that your files are going to work, all right? So I'll just show you by doing one, all right? So the way I'm going to do it is say, all right, the peak to peak of my noise is 521 millivolts. All right. So I have created a Google Sheet or with various tabs. So I'm just going to label it VP 521. All right. Then I will go to where I had that file. And I had just called it full width half maximum. And I'm just going to cut and paste it here. Now, in order for it to be processed, you have to publish the link. You can't just give it a link. You've actually got to do it in a special way. And so what you do is File, Share, Publish to the web. We don't want the whole entire document. I just want VP 521. I don't want to publish it as a web page, but comma separated values, and everything else is fine. And we publish, and then I copy that link. And then sometimes what I do is I just go URL, and then I paste it in. So this overwrites that. All right, and then we just play it. I'm just going to run it one more time just to make sure I'm getting the right thing. Okay, so what we got from here is the theta, the RMS, which it has to calculate, right, of 0.41. All right. So that's really and effectively the peak to peak of the input noise. But RMS is a better, more reliable measurement. All right. Then you close that. And then I have another one, full width half maximum results, right? And in fact, I don't have a 0.521. So I've actually done this all the way through. So I'm just going to insert a row, and this was the peak to peak, right? And I can verify it. Yep, it was 521, right? The theta that I measured, just cut and paste, and then I'm going to go back and get. I was running a local copy. And the full width half maximum is 659. Right. Now let's just take a brief moment to explain that. All right. So I had to transform this data, but this is almost like a FFT or spectrum analysis that we did earlier. Right, let's look at it. Where is it? Tools, spectrum. Okay, and then we're on linear, channel B. This is the DC offset here, which I actually I remove for analysis. And let me zoom in here if I can. All right. And you can see this is the noise, and it has a frequency, has a kind of a peak in frequency, or peak in magnitude, and then it rolls off, right? But these spikes are, all over the place. So what we do is we take the power spectrum density, which really is based on the FFT, right? And what it does is it multiplies, it squares all the values, and then averages them over the whole frequency spectrum. So you get this, which is a little more, it's still noisy, but you get a little more, it's a little more reliable. But you can see that, it starts high and then goes low. And then there's a curve fitting program that fits a Lorentzian curve, and it plots it. And so the full width half maximum is really, the full maximum here is about 0.2, so half maximum is about 0.1. And so what is the, essentially, what is the frequency width at half maximum? And it turns out it's 659. And so we're going to do this again and again, right? In fact, I can go back here, and I'm going to take the biggest one, right? So I'm just going to go again, File, Share, Publish to Web. I just want 938 CSV. It's already been published. There's the link. I come back here. And then rerun it. And now you can see that the full width half maximum is farther out, near 2000. Here, full width half maximum 1700, and theta is bigger. All right. And so what we're doing is characterizing the stochastic resonator. we just need to do another plot of that. And I'm just going to show you on my local copy. Okay. So basically we get the theta, which is the RMS, and the full width half maximum by basically we keep increasing this, recentering that to make sure it's still working, right? But see how it's mostly low right now. I can, or what I'll do is I'll just do a bigger one. All right, so I've increased the noise. Right, I've increased the noise. The peak to peak now is 6. The average, it's a little high compared to what it was, so I can try to bring it down. 2.5, and I can bring it down again, 2.48. That's really about where it can be, okay? And then I would re-export that waveform, cut and paste it into all of these various ones, measure the results, put them here, and again I have to publish this one to the web, copy the link, and in this other program, right, you put in that URL, which I'll make a link to, and I will run it. Okay. So what we have here is this is for each theta, and we plot 1 over theta. We have a full width half maximum plotted on a log scale. Okay. And those are all the points I measured, and they don't all fit on a line. And the thing is I can't really measure for a long time, so these measurements will bounce around. Sometimes what I do is I take 3 in a row and take the average, right? And then I didn't do it in this case, I just did that. So it's relatively, a straight line. Now it starts to deviate up here, so I didn't bother going any faster. But the fact that I can extract a reasonable straight line, right, on this plot will give me, that slope actually gives me the approximated well depth of the stochastic resonator, which, yeah, you got to go and read up what that is. All right, but that really means that this is a stochastic resonator. Then the next thing would be to put in a sine wave, and we can measure how well it detects the sine wave. But this is one step in proving that this is a stochastic resonator. And yeah, at these levels, this noise is very small, so things do bounce around, right? And it is a real, noisy measurement, so it's not going to line up on the line. Anyway, that should be, that's where we're headed. I just got to write it in the lab manual, but really you just go and you increase the amplitude, right? But now it's down too low, so I just back off until I can get the average back near 2.3. I'm just clicking one click. All right, so that's 3.8. I'm at 4.7. So the peak to peak is 1.8, right? Then I would just export it to the waveform, load it in, run the one file, and just create, making, and doing that. And yeah, I found I was starting to, you can go higher, but at about 0.938, right, it was starting to peter out. And then even, something's not exactly right here. I think I wrote something down wrong. But anyway, that's it for that part of it. You actually should be able to follow those instructions. It's a little bit harder than having a lab manual, but creating that full width half maximum is, you're working on the research project right there, because I want to know, we're all kind of doing the same thing, but are we all getting, are we getting that slope? Is that consistent? How repeatable is this experiment among all you researchers? That's it.